Welcome you all in this talk on separable spaces. It is well known that the rational numbers or irrational numbers are densely packed along the real line. This phenomena can be characterized in terms of distance by saying that every point of R is at zero distance from set of rational numbers Q or from the set of irrational numbers R minus Q. The concept of closure enabled us to write this density property by the formula that the closure of Q is equal to R or the closure of set of irrational numbers is equal to R. So in this talk, we extend the idea of density to an arbitrary metric space. We discuss some other properties of a metric space known as topological properties, such as countability, separability, and bare category theorem. Let us take O is the family of all open subsets of a metric space X. So what I am taking O as a family of all non-empty subsets of a metric space X. Then a subfamily B of O of open subsets of X is said to be base or basis for O if every open set in G is the union of members of B. Further, if the subfamily B is countable, then it is called countable base or countable basis for O. Before giving the examples of a base for a family of open sets, we mention the following characterization of a base. So we have the following theorem which gives the characterization of a base for a family of open set. So let us take let O be the family of all open subsets of a metric space X. A subfamily of O is a base for O if and only if for every point X belonging to an open set G there exists an element Bx in B in the subfamily B such that X is in Bx and Bx is a subset of the open set G. So this is the characterization of a base for a family of open sets. The proof is very simple and we can see it very easily. So let us take B be a base for O and G be any open set in X. Then of course G must be an element of O because O is the family of all open subsets of X. So G must be in O. Then by the definition of a base, G is the union of members of B. So let's take X. X is in capital G, and since G is the union of members of B, there exists a set Bx in B such that X is in Bx and Bx is the subset of G. Conversely, let G be an open set, any arbitrary open set. Then by hypothesis, for any point X in G, there exists an open set Bx in the subfamily B such that X lies in Bx and B is the subset of G. Clearly, G is equal to the union of all Bx where X lies in G. So, on each G we will have an open set, and if we take the union of all such open sets which is equal to your G, and now since G is an arbitrary, G was arbitrary, every open set is the union of members of B. Now let us see some examples of a base for the family of all open subsets of a metric space. So again we start from a very a very usual metric space, that is to say the set of all real numbers, then the collection of all open sets, okay, whose endpoints A, B are real numbers. So this is the collection of all open intervals, and this collection of all open intervals forms a base for the family of all open subsets in the usual metric space R. If the endpoints A and B in this interval are rational, then this collection B, where A and B are rationals of all open intervals, forms a countable base for the family of all open sets in the usual metric space. Now take an arbitrary metric space. So let X be a metric space, and let us take a collection of open spheres. Okay. So collection of open spheres with center at each point of X. And then this collection of open spheres forms a base for the family of open sets in X. Indeed, let X be a non-empty open subset of X and X is in G. Then, by the definition of an open set, there exists a real number R is greater than 0 depending on X such that X lies in SRX, open sphere with center at X and radius Rx, and this open sphere contained in G. And then by the characterization which we have just seen, G is this family is a base. Now take another example where we are considering X is equal to Rn with the following metric: dpxy is equal to summation I runs from 1 to n mod of xi minus yi raised to the power p whole raised to the power 1 over p for all p is greater than or equal to 1, where x and y are the element of Rn. Let us take R is greater than 0, any rational number. Okay, then the collection of open spheres with center at X and radius R, where xi's, all these xi's are rational and R are rationals, and of course here we are taking R is rational. Then this family of all open spheres with rational centers and radii and rational radii is a countable base for the family of all open sets in X. Now take a discrete metric space X, then the collection beta of the form of this form, and which the element of X the elements of beta consist of singleton set, and as we have seen that the singleton sets are open set in the discrete metric space, and so therefore this B is the collection of open subsets of X, and this collection forms a base for the family of all open subsets of X. And if X is countable, then this collection is countable, and in this case B is a countable base for the family of all open subsets of X. Let X be a metric space, and it is said to be a second countable space or second axiom space if there exists a countable base for the family of all open subsets of X. So now one can say that we are introducing the concept of second countable space. Where is first countable space? Okay, why we are starting from the second? Why not from the first countable space? So the answer is that because the second countable space, the definition of the second countable space is based on the base, and we are in the continuation of the base, and therefore we are defining the second countable space first, and we will define the first countable space later.